Okay. Good afternoon, everyone. I think we had nice and big lunch today. Today I will talk about AI assisted focus workflows and the script open. Even though I'm presenting today, there are two engineers who have been contributing actively in this work. This is part of the Gyeongjin team. They are actually the hard workers for this project. Thanks them for their hard work. Okay, back to the topic. The key point of my presentation is this. We do not let AI directly edit AutoStar AI style. Our approach is to expose commercial AutoStar engineering capabilities to command line and script. Use knowledge base and ARTA model integrity as guardrail, and let AI orchestrate the full loop from configuration to build and virtual ECU verification. Okay, here consider a seemingly simple requirement, adding 3 signals to a project. I depicted the exemplary number of files and steps and checks to verification. Yeah, just 3 messages, but it seems many than the size of the signals and the actual program, right? Actually, such as 5+ files, including a database and the system description and the ECUC and COM and PDUR. Sometimes we may need to add other modules if we have some signal which has a connection with the other features such as E2E or secrecy, right? And when we imagine AI, the application, if we use AI agent to workflow with this, say, let's say if we have 500 steps to follow, and if the AI makes a critical error on step 1, it doesn't matter, it executes the next 499 steps correctly. It results in the cascade of errors and wasted token consumption, focusing us to discard of output and start over, right? So expanding actually that kind of big significant tokens to generate the result is often the wrong approach. Many of these issues are deterministic and could be solved more efficiently, such as a single well-defined automation script or a strict validation rule, right? So finally, there is a verification bottleneck. Even if the AI generate or complete the task, how do we establish trust? Human engineer is still required to review and validate the output in case. Then that negates the assumed productivity we get, right? Okay. In this example, the AI request, like adding 3 signal, sounds simple, but in AutoSAR, it propagates the across signals, system signals, PDUs. So the real challenge isn't merely executing the mechanical steps. Actually, it's understanding the downstream impact on affected modules and determining the correct update sequence and respecting strict architectural constraints. currently, end-to-end AI approaches gaining popularity, right? But can we realistically use a pure E2E AI solution for AutoSAR with a sufficient degree of trust or stability? Even if it generates an output, how do we establish trust? I was told the reality, actually the industry is facing some friction trying to achieve this reliability. So how can AI agents actually help us? We need to guide the AI to solve problems in structured, reproducible, and AutoSAR compliant way. So the key is setting up strong validation guidelines, and we can call that guardrails. There is no silver bullet, but this raises an important question. How do we actually build these guardrails? Where do we get the right knowledge to guide the AI? Yeah, that's. So I added that for wasted tokens. I wanted to emphasize this. Okay, generic AI alone is risky, I think, because it does not understand the AutoSAR model and domain fully. We cannot guarantee it fully understands the AutoSAR model, and it easily loses its context during complex tasks. In fact, there is a critique in the industry right now. AI might work rapidly, quickly, diligently, but it might increase entropy just as fast. On the other hand, relying on the right side on existing tool chains is also limiting. Many operations rely on the UI-based jobs, and that's locked behind the manual workflows. So our approach, I think others might choose other ways, other paths, and our approach was to make the domain toolchain programmable first. So once we had the programming foundation, we need the rules. Over the years, we have accumulated some quite amount of the data and know-how from supporting our customers. We thought that this real-world experience had to be used as guardrails and guided paths. So given these limitations, our first step was not to attempt training a new foundational AI model for AutoSAR. Instead, we looked at where the actual engineering knowledge already exists. It's in right design, such as in our toolchain, MobileGen. So in our toolchain, specifically within its validators and the generators and workflows. Yeah. Historically, in our industry, deep AutoSAR expertise is passed down almost like apprenticeship as a tribal knowledge. We realized that it could capture this unwritten experience and structure it into an AI accessible knowledge base, such as an MCP. Yeah, we could elevate our support for all customers. Therefore, our primary goal was to expose the core capability of MobileGen through command line and scripting and APIs. Once the domain capability became the pure executable, then AI can step into the role of orchestrator. It doesn't guess the rules, given the rule or guardrails, so it can orchestrate the execution using toolchain and the structures knowledge base. And more, AI models are evolving very rapidly, right? So we do not try to own every layer of the AI stack. We borrow the fast-moving AI layers and LLMs, such as and the agentic orchestration loops also we can borrow, but we own the AutoSAR specific part, yeah, domain knowledge and project context, yeah, command line script access to our tools, and the validation guardrails, and the for the validation, the virtual ECU verification loop. Yeah. In other words, AI can accelerate many engineering tasks, but still, I think trust comes from the deterministic validation. So this is one of the example showing our choices. So in this here, if we let AI to edit directly the ARXML text, actually sometimes it breaks the references, and also it can make the schema invalid. And actually, as you know, as you see, it's more than 80K lines for one module actually, and it's not big one. It's much bigger in real ECU development. And in here, we can say yeah, more than 10,000 parameters and more than 2,000 containers to deal with. So it can easily lose its context and exceeds its token usage, right? So as we saw on the previous slide, forcing AI to process and memorize massive XML structures is inefficient, and sometimes it's risky. So in reality, our actual goal is often very simple, such as just doing one single parameter change. Yeah. Oh, sorry. Yeah, that one. Sorry. So rather than letting the AI struggle with the raw text, we can achieve stable, targeted modification with just a single line of command line or script. So in our path, the AI does not directly edit ARXML. Instead, AI generates or selects specific command lines and or script operations. Yeah, these operations are then executed through the RTOP model layer and immediately checked by the MobileGene's built-in validation. Finally, the result is verified through actual build and virtual testing. So in short, AI is not acting on XML text editor. Yeah, as an orchestrator, it gives commands to our toolchain. So why we chose this way, and why scripting? So first, to make domain tools programmatically accessible, maybe we can choose other ways. But choosing this scripting, I think as a building block to enable human and machine universally access and further tooling support. And to make engineering operations repeatable, auditable, and executable by human or AI. And why we chose open source? We don't have to invent wheel again, right? Yeah, its concept is same with the AutoSAR, right? So already existing technology can handle this. So we avoided developing again, and also vendor lock-in. We hopefully we don't want that, right? So we chose open source for it, and it's also helping to lower learning curve because we have already known the technology which is open, right? So with that, I think we opened the bridge to the gap of domain knowledge and script handling and AI. So we can say this is the bridge we built. So it's between the programmable layer and AutoSAR domain capabilities. On one side, we have the programmable layer. on the other side, we have real engineering capabilities, such as DBC import, harmonize, or configuration feature, or validation, or code generation, and the build and virtual execution, right? And um, once that capabilities is callable via command line or script, AI can use that. For this, we made almost all tool features scriptable, from simple operations such as changing parameters or opening projects to a complex wizard-based one such as data mapping. So open source scripting keeps the bridge flexible. RTOP-based model access keeps it schema aware, and MobileGen, our toolset, provides the commercial engineering capability behind the bridge. Yeah, this is the full architecture. It's you can see the AI agent and others as building blocks, right? So we designed it with the concept of building blocks. That can be switchable or maybe added, extendable, right? And maybe if technology change it, then we can change that specific block, such as if we don't use RTOP anymore, such as we can switch that to other technology, right? So we thought that is a concept of building blocks. So the AI agent is responsible of reasoning, planning, and script generation and executing tools. And it does not directly modify the XML, and it uses its knowledge base and MCP for the AutoSAR or our toolchain knowledge, and then generate the script to use the APIs to do actual work on top of the RTOP library, which is community-based source code. And these open source one, Eclipse EASE is supporting tool for library for the scripts such as JavaScript or Python. So we can choose any of the technology script language for this on top of the EASE. And MobileGen validation is another block to act as a guardrail for it. So knowledge guides the AI. The bridge translates the intent, and the underlying RTOP vendor validation ensures schema integrity and the configuration correctness. Yeah. Okay, this is the overlook of the engineering loop of us. So first, it analyzes the project model and tool context. Then it plans the affected modules and execution order. And it executes command line commands or scripts with backup and generates code, builds, and validates the output. Finally, it verifies with the such as a virtual ECU. And if something wrong on error, it doesn't stop that point. Actually, it can be feedback to this plan again. So the errors or other messages or logs can be reused for the auto recovery of this loop. So if we keep the loop until we achieve the intended requirement, then it's done. So after doing this, we realized that it impacts engineer role. So let's say manual configuration. Engineers were stick to editing the each files, and the manual cross-reference tracking. Sometimes we do it, and the build and validation by hand. And for this AI assist workflow, engineers defines requirements, and AI executes configuration, and the engineer reviews and approve, right? And I think it will be becoming like this. So pipeline, AI will do the pipeline, and engineer sets constraints, and human intervent is only exception. And maybe we can say he will be judged to AI output or AI performance. So I think anyway the role of engineer will be more high value judgment job, and the lower risk one and repetitive work can be switched by the AIs that can be helpful to engineers and both company. And now let me show how this work in a workflow. So here a new DVC file is received and need to be integrated into a project. The agent analyzes and with the dependency graph, and identifies affected modules, and resolve the execution order, and check project specific context if required, and the policies. If something is ambiguous, yeah, it can ask the engineer first. So before any change of the project or area XML, the agents creates a plan first. And in this screenshot, it's actual screenshot of the AI workflow of ours. So you can recognize AI is planning. It collects project context, and identifies the modules and its environment. Such as in here, in validation, we skipped the run validation API because it's in C Studio mode. Actually, in UI mode, we can run the validation without running another command line scripting. So it's skipping that because of that. That doesn't have to be run in command line mode. If required, information is missing or something, then it can ask. So in here, it plans like this. So after planning, the agent executes the workflow through command line CLI and script. You can see the AI analysis input here, such as, and execution is, I can say it's traceable because you can see logs and all the commands it run, right? So it's repeatable, and logs and model summaries also. And those outputs are also used as a feedback for the next step of the loop. And next is the agent checks the build and validation results. This confirms that the current requirement, DBC integration steps were applied, and the project can be generated and built successfully. So scenario 1, I present now, closes as successful configuration and build. So next one is, so far we reached successful configuration and build, right? But the configuration and build are necessary, but it's not sufficient. For ECU software, the real question is whether the configured behavior works as intended. That's why we extend the AI loop to runtime verification. Yeah. Yeah. Next scenario is focused on the remaining part. How the agent handles failures, revise the plan, and close the loop through build and verification through virtual ECU. So in this scenario, we assume there is a build error, such as a generation error or build error. In here, it's a build generator error. In manual work, we need to investigate what's the root cause, and that means another round of investigation. And this loop failure output becomes structured feedback. The agent reads validation or build logs, identifies likely causes, and propose a revised plan. Um, so instead of blind retry, the agent uses its validator and build output with the evidence, and also the MCP provides the knowledge base to search the likely errors or reasons, and it parses the logs and affected log modules or model elements from the log, and revise the execution plan. In here, we can see it's proposing to change some ID for correctly changing it. Then it generates a correct script, generate or select, and the reruns that tool change steps and checks the results again. It's agent loop, not simply repeating the same operation. It's using tool feedback and improve the plan of it. Before runtime execution, we check whether the XML is correctly reflected the generated code. The agent uses assertion derived from the LSM configuration. In here, it's showing a script, Python script, to check whether the generated code is as intended. There are some points to check. AI used some scripting for checking that. Yeah, that gives us an additional verification point between configuration validation and runtime behavior. And the final verification step in this loop was the runtime seal test in Mobilegen vStudio. This allows us to execute the configured ECU behavior in a virtualized environment with virtual OS and virtual CAN, Ethernet, and virtualized MCAL. The agent then analyzes the CAN log by seal analysis skill with the Python script, and compares the expected output with the actual runtime output. In this example, the runtime check confirms whether the expected CAN signal is transmitting as intended, and also as the intended period. So the loop ends with successful behavior with the virtual verification. Yeah, this is how we close the loop with the guarded auto recovery. The agent can revise plans and rerun scripts, but every change must pass through the defined guardrails. These guardrails include schema integrity checks, reference consistency checks, module level validation, and additional validation checkers for system or domain level issues. Those checkers can inspect not only configuration but also generated artifacts such as a code, configuration output, or linker script. That's all based on known issue patterns. Yeah, combined with the virtual verification, we can extend this loop to this verify. So the loop check not only configuration correctness, but also the resulting behavior is executable and valid. This is our observation with the demonstration workflow. The value was not simply the faster execution. Actually, it was fewer uncertain iterations. The agent helps reduce the time spent searching for what changed, where to look, which module is affected, and what action should come next. Uh, that means less rework, shorter engineering lead time, and a faster path from configuration change to verified behavior. Okay, so trust comes from the multiple layers. First, scope and order are handled by dependency analysis instead of memory and guesswork. Second, the project rules can be provided as knowledge context. Third, tool execution becomes traceable because commands and scripts are logged. Finally, error handling becomes a loop. Failure trigger diagnosis, plan revision, and re-execution. AI generates plans and scripts, but schema validation, reference integrity, and the mobile validator enforces correctness. So let's summary for this presentation. The first takeaway is that domain-aware execution. In with the general AI, we added domain knowledge base and a command line script and API, and that made system or domain-aware agent. So with this, AutoSAR specific knowledge transforms a general model into a precise engineering tool. Yeah, and the second takeaway is full cycle automation. That automation should cover the full engineering loop, not only configuration. So until the runtime verification, we could verify that. The agent owns the entire pipeline, so that it can verify until the actual implementation. And the third takeaway is that engineers move from repetitive execution works and to workflow architecture and engineering judgment. So with the AI help, we can consider role expansion of the engineers. So AI is not a magic; it's an engineering. We are to guide the right path to it look like magic. With the guide and the appropriate engineering, we can make the AI looks like magic. Our choice was to make AutoSAR domain capabilities programmable and to keep model operations within validated guardrails and to enable AI to orchestrate the full engineering loop. So plus, we use our knowledge base guiding AI to correctly tackle AutoSAR problems. And the bridge is open. The workflow is programmable and validated and extensible with these building blocks. Programmable, we can say command line and scripting and guardrail, RTOP and mobile validation and knowledge base, executable, build and virtual ECU verification. What we show today is one workflow example, but the pattern is, I think, more general. It is a practical pattern. Make the toolchain programmable, keep model operations guarded, and close the loop with the build and virtual ECU verification. So with this, we can extend our the coverage with adding more plugins or changing to new technology. So for example, with the bridge open, using open source scripting and community source AutoSci infrastructure such as RTOP, we can apply AI to many other opportunities. In yeah, in here, what we have shown today, and next is actually a CI/CD and multi-issue orchestration, and requirements traceability too, and then also the functional safety and security with the domain knowledge and tools such as skills or MCP we have in our knowledge base. So in short, AI orchestrate, guardrail validate, the toolchain execute. That was our concept, and using the open source and the community source such as RTA was the key part of implementing this. Yeah, thank you. So if you have questions, yeah, please let me know.
Yeah, thanks for the great presentation. I'm Marco Vier from Vector Informatik. I have a question regarding the kind of abstraction that you provide with this API. So is it, let's say, on AutoSAR configuration attribute abstraction level, or do you provide some additional abstraction?
Okay, as a basis, we provide the AutoSAR level abstraction, such as changing parameters or getting parameter values, and also it extends to more complex work, such as wizard-based ECU extraction, data mapping, and task mapping to those features. What we had already as a tool, we implemented all as a script or APIs. Actually, we used APIs and then connected to the underlying MCP server to support the scripting language such as Python. But we can change that language too. And also, while we were supporting our customer, such as patching the project, we had to deal with other file formats, such as linker script or the project related version files or others. So some we applied non-AutoSAR APIs, and that could also the feedback to our MCP or AI. Yeah, thank you.
Yes, thank you for your speech. My question is your methodology or your scripts or tools, does it works well in a large amount of project or with a real project? Because you also mentioned we may be under the context window of LLM. So I don't know whether it's behaved.
Yeah, so during the applying that, and when we tested too, we used the production level. Actually, our customers, the configuration as an example. So we saw that if we use conventional AI alone to apply some change or fix, we observed many times of kind of a endless loop, creating entropies, such as if some parameter is changed, then actually it was not to change. Actually, the actual issue was in the other side, and then it goes into the very long way. So we observed that starting over again was better, and because of that we started it. So we can say we tested with bigger configuration.
I have some additional ones based on your answers, because I think the key problem is to understanding the whole project. If we build AI XML or build a configuration from scratch, I think the whole should works very well. But if we want to do some modifications or on the current project, it may face that problem. So I think that's a key problem.
Yeah.
And,
So during supporting our customers, actually, we have been in this the field more than 20 years. So applying AutoSAR and supporting our customers, there were many issues, or we can say knowledge now. Such as there are many DBC file changes, such as we can say once in a month for one ECU, such as. Then many time, yeah, it's happening to real project, yeah, such as changing small amount of the message or parameters. So we are piloting with the customer for this kind of work, and we think that's working.
Okay, so that's another is about if you will do in such way, that means you will provide your expertise experience into all those skills, right? So
Yeah.
will you provide these skills to your tool user? I don't know what your tool or scripts
Yeah.
whether provided to the internal end users or just in Hyundai.
We can say we are seeing how effectively provide our value to our customers, because the customer the information is very important to keep secretly, right? So keeping that security is a kind of tricky point, such as having a separate DB for all the customers, or having combined one and eliminate all the detail or specific project specific information. That is kind of a tricky one. So we are yeah, communicating with our AI team and other infra to how to support our customer well in that kind of constraint. That is current status. Okay, I think that's all for today. Thank you for your time. Thank you.